In this video, we're going to do example 6.3.1. We're asked to suppose that S is a solid bounded by x squared plus y squared is equal to 1, z equals 4, and z is equal to 1 minus x squared minus y squared. We're told that the density at every point in S is rho of x, y, z is z times the root of x squared plus y squared. And we're asked to use cylindrical coordinates to find the total mass of S. So to find the total mass of S, of course, we want to find the triple integral over S of our rho function x, y, z dv. And we're going to use cylindrical coordinates to set that up, or cylindrical coordinates, apparently. I'll fix that in the version that you are given of these notes. So let's go and draw what these figures look like. So z is equal to 4, we know that's a plane. X squared plus y squared is equal to 1, that's going to be a circular cylinder. And this is a paraboloid facing down because the coefficients are negative. So if we draw that paraboloid first, we know that its top value is at 1. So if we draw this here, it's got a circular base because when z is equal to 0, when z is equal to 0, we see we're going to get x squared plus y squared is equal to 1, which is exactly the cylinder that we want. So x squared plus y squared is equal to 1 matches at the base, and we're going to go up only to a height where z is equal to 4. So if I add in some axes through this, I have the solid here, which is above the paraboloid and below the cylinder. So let's get the rest of the axes up here. And this is where z is equal to 4, and this is 1 and 1. So we're talking about the area inside, not the area, the volume inside above the paraboloid and inside the cylinder. So that volume in there. Now, that volume has a density of this, so we need to describe our region. We know our bottom function is going to be u, which is the paraboloid, so u of xy, u1 of xy is 1 minus x squared minus y squared. In polar coordinates, that's going to give us 1 minus r squared. Our top function is going to be u of xy, which is just going to be 4. And so we have to describe our shadow region. Our projection down into the xy plane is going to be that circle. And so we know exactly how to describe that circle in terms of polar coordinates. So that region there is our projection into the xy plane. And in polar coordinates, that can be described as the integral, not the integral, as the interval of theta from 0 to 2 pi, and the radius going from 0 to 1, which means that our triple integral is going to be in terms of theta, so from 0 to 2 pi, in terms of r from 0 to 1, and in terms of z, we want z to go from 1 minus r squared to 4, and then we have to translate our density function in terms of r and theta. The z can remain, so we're going to have z times, and this, the square root of r squared plus y squared, is going to be r, and then r dz dr d theta. This part here is the dv. And then we just evaluate that integral. So let's clean that up a little bit. The first thing that I see is there are no thetas anywhere here. So this, as far as theta is concerned, is a constant. I'm going to bring that out. Or it looks like I'm going to bring theta inside instead. In other words, I'm saying we can do this. The integral from 0 to 2 pi of d theta. Then we're going to have the integral from 0 to 1. And I'm going to integrate. So we have r squared here. I have to integrate z dz. So I'm going to get 1/2 z squared, which is going to go from these bounds of 1 minus r squared to 4. R squared to 4, and then dr. So let's move down to give ourselves some more space here. The integral from 0 to 2 pi of theta, well, that's going to give me theta, 2 pi minus 0, so I'm just going to get 2 pi there. The integral from 0 to 1, I'm going to bring out this 1/2. That's a constant. I'm going to bring it right out in front, so that's going to be 2 pi over 2. Those 2's will cancel. R squared, and then I have to evaluate using the fundamental theorem, top minus bottom, so 4 squared minus 1 minus r squared dr, and then I just have a single integral now to evaluate. So let's go and get that done. So this is pi times the integral from 0 to 1. We've got r squared, and this is going to be 16 minus 1 minus 2r squared plus r to the 4th dr, or pi times the integral from 0 to 1. What are we getting here? 16 minus 1 is 15 times r squared, so 15 r squared, minus, so I'm getting plus 2 r squared times r squared, r to the 4th, and then minus r to the 6th dr, which I should really be writing equal signs all the way down here. So pi times, now we can anti-differentiate. We're going to get r cubed over 3, 15 divided by 3 is 5, plus r to the 5th over 5, minus r to the 7th over 7 from 0 to 1. So pi times 5 times 1 plus 2/5 times 1 minus 1/7. All of that minus 0. And so we need a common denominator here. A common denominator is going to be 35. 35 times 5, 150, 175. 175 plus 14 minus 5, which is going to give me 170, 184. 184 pi over 35, and this is whatever units of mass, because we were told that we had a density function. So the moral of the story is this would have been excruciating to evaluate in rectangular coordinates, right? Because this projection down in the xy plane is a circle, which would be a nasty root function, which to integrate over would probably require trigonometric substitution. So much easier to describe, especially since we have a cylinder, to describe the region in terms of cylindrical coordinates and to use them to evaluate and to find the answer.